We already learned the Fourier analysis for periodic continuous time signal. Now we try to extend the continuous Fourier series from periodic version to non-periodic continuous time signals. So we're going to start from Fourier representation of non-periodic continuous time signal. So before we do that, we want people observe the difference and the relationship between periodic continuous time signal versus its non-periodic counterpart. Imagine that if you can increase the period of this periodic signal, you can increase, then the distance between the two rectangle signal will increase. And if we make the period approaching to infinity, then this periodic signal will become a non-periodic signal. So based on this observation, we can write the relationship between x of t, non-periodic signal, and the tilde x of t, a periodic signal, in this relationship. So this will be the foundation of our following derivation. So this is what we learned, the forward continuous time Fourier series. And if we put this part into the other side of the equation, and we try to take the limit, the fundamental period approaching to infinity, then this equation will become into this format. And we can move the limitation from the outside into the inside of the integral. And this will be the new definition of this limit. If we notice that the interval between the spectral line of Cn is equal to omega sub none, which actually is equal to 2 pi over the fundamental period t sub none. Then if t sub none approaching to infinity, then n times omega sub none will become a continuous variable. Here we're going to use omega to represent it. Then this equation, take the limits, will be equal to this more simplified definition. And we use capital X of j omega to represent the results of the integral. So this is one way to do the extension from the periodic signal, the continuous time Fourier series for periodic signal, to continuous time Fourier transform for non-periodic signal. And what about the other way around? This is the inverse Fourier series. Then what is the counterpart for non-periodic continuous time signal? Before we do the limitation, take the t sub none approaching to infinity, we want to first rewrite the equation into this format so that we have these two terms in multiplication. Now, we can break this one. This is equal to 2 pi over omega sub none. So this can be transformed into this equation. And now, if we take this relationship between the periodic signal and non-periodic counterpart, we can plug the expression into the limit. And we know that this is given in the previous slide. And this will become into this format. We know that when capital T sub none approaching to 0, n times omega sub none will become omega, and the interval between the spectral line will become an infinitesimal value. We use d omega to represent it. Then this equation becomes this integral. So these will be equal to the original signal, non-periodic continuous time signal. So to summarize the previous two slides, we can write this one out as the extension of the Fourier series to non-periodic continuous time signals. And this will be defined as continuous time Fourier transform. And the other way around will be defined as inverse continuous time Fourier transform. And this is the important extension from Fourier series for periodic signals to Fourier transform for non-periodic signals in the continuous time domain. And we often use this symbol to represent these two signals are a pair of continuous time Fourier transform. Very similar to our explanation or the representation of periodic signals using Fourier series. So this is one way to do signal representation using Fourier transform. So the meaning or the significance of this equation actually is any continuous time signal, non-periodic continuous time signal, can be represented as a linear combination of infinite terms of imaginary exponential signals. And the coefficients of the linear combination actually is defined as spectrum, can be calculated using this integral. And we call this integral spectrum of continuous time non-periodic signal x of t. And also very similar to what we learned in Fourier series, this spectrum is in general a complex function. It will have two independent components. So the amplitude part will be called amplitude spectrum, and the phase part will be called phase spectrum. Non-periodic signals may or may not have Fourier transform. For those who satisfy the direct conditions, they will have Fourier transform for sure. So the direct conditions include three criteria. The first one is the original signal must be absolutely integrable on the interval of integration. The second is the signal must have finite number of extrema, and it has finite number of finite discontinuities. So very similar to the direct conditions for Fourier series. Again, the direct conditions, they are sufficient conditions, meaning a signal satisfy all these criteria will have Fourier transform for sure, but even for those signals, they do not satisfy all these criteria. They may have Fourier transform as well. And here's one example. We try to figure out what is the Fourier transform for this non-periodic rectangle signal. What we can do is we can use the definition directly. So we can put the x of t into the definition and do the calculation. And here is the results. And this will be the spectrum of this non-periodic continuous time signal. So here is the plot. Please pay attention that in Fourier series, the periodic signal in the time domain corresponds to spectral lines in the frequency domain. But now in Fourier transform, non-periodic signals in time domain corresponds to continuous spectrum in the frequency domain. It's critically important time frequency correspondence in here. And there are some characteristics as well. Again, we're going to use rectangle signal as one example. First of all, the spectrum of a non-periodic rectangle signal is continuous. We already mentioned that in the previous slides. Second, the signal with limited duration in the time domain, corresponds to unlimited spectrum in the frequency domain. This is once more a time-frequency correspondence. For rectangle signals, we can also define effective bandwidth as well for the non-periodic version in here. And it is the same definition, 2 pi over tau. Tau is the duration of the rectangle signal in the time domain. And the effective bandwidth in the frequency domain actually is the origin and the first zero crossing point in the frequency domain. And here's the formal definition. Omega sub capital B effective bandwidth is equal to 2 pi over the duration of the rectangle signal in the time domain. Thank you.